Everyone. And just so you're all aware, the meeting is being recorded. We will be making the slides as well as the video public. So just something to keep in mind for the day. So welcome to the Variorum lecture series. This is the first module of a series of 2 modules. And we will be repeating these 2 modules in weeks 3 and 4. So in case there is a time conflict and you prefer a different time, you would have the option to attend it at a different time. So the team that is presenting today is from Lawrence Livermore National Laboratory. I am Dr. Tapasya Patki. My colleagues here, Dr. Anirudh Marathe and Dr. Stephanie Brink, will also be presenting. And we also have Dr. Barry Roundtree, who has been a great part of this team as well. So all 4 of us are the key contributors to Variorum. And Stephanie is the lead architect of Variorum. So you will hear from her in the second half of this, of the lecture series today. So let's get started. And let's look at what the rest of the day looks like. So this is going to be 1.5 hours. And we will start by introducing some challenges in power management and the HPC Power Stack initiative. This is going to be about a 20-minute introduction to general power management challenges. After that, we will dive deeper into power management knobs on different architectures. So we will look at Intel, IBM, AMD, NVIDIA, and ARM architectures. We will be looking at how the underlying mechanisms for each of these different platforms and architectures expose power management knobs, including power control and power measurement knobs. And after that, we will introduce the Variorum library and its API and show how it exposes these different platforms and knobs in a seamless and vendor neutral manner. And we will leave some time for questions at the end. If you have any questions along the way, feel free to post them in the chat. I will not be monitoring the chat because I'm presenting for the first half, but I'm assuming that Stephanie or Anirudh, if there is a question that we need to answer immediately, then feel free to interrupt me and I can pause and answer that. And we can do the same in the second half as well. If not, we can leave the questions towards the end and we can have a nice discussion on some of the topics that we've presented. So with that, let's get started. So as most of us here in this group, at least, are familiar with HPC systems, we know that they include compute nodes, IO nodes, and network. And here's a picture of IBM Sequoia from one of the past supercomputers here at Lawrence Livermore. And the thing to know about power management for HPC is that there are 2 different components. There is static power management and dynamic power management. And there are some components that we cannot manage. So there is definitely the base power or the idle power that we need to essentially bring up the system in the machine room. So this is typically your network fabric, which includes your compute nodes and IO nodes at the bare minimal power that is necessary to keep them operational. So that idle power stays constant, and we really cannot change that. On top of that, there is static power management, where we look at setting or getting power in an environment where we are not changing the power cap much. So, these changes are made at system bring up or during maintenance cycles, and then nothing changes after that during execution of jobs. The third aspect is dynamic power management, where during a job's execution or during a user's allocation, they can go in and make changes to power control knobs and energy knobs and temperature knobs and so on and so forth. And that's an important aspect of power management. So just keep those 3 distinctions, idle power, static power, dynamic power, in your head today as we walk through some of these examples today. Most of the focus of this work would be on enabling static and dynamic power management. We would not be looking at network fabric today. We would not be looking at IO nodes. We would be focusing on primarily compute nodes and different compute components, in some cases GPU power and memory power, to understand these different power management options. So this work today has been is being presented as part of ECP. So I wanted to mention and thank ECP for their support. Though this work is being conducted as part of the ECP Argo project, and there are some other synergistic projects that we will talk about in module 2, which include Flux, Caliper, GOPM, and COCOS. I should edit the slide there to reflect COCOS as well, and some other synergistic projects in terms of workflows and applications called MUMI and E3SM. So we will cover some of these in module 2. Today's focus is primarily going to be introduction to power management, followed by power knobs, followed by Variorum API, as I discussed. So let's start by looking at system-wide and dynamic power management. So what do we mean by that? For every supercomputer, there are various levels at which you can manage power. So there can be a site level requirement where there's a cluster level power bound, which is derived or obtained based on the requirements of the site. So this could be the electricity service provider having a certain contract or certain set of requirements on the supercomputer center. This could also be wanting to be more environmentally friendly or wanting to address some peak power pricing related challenges within the center. So these are site level requirements. Those site level requirements typically dictate a certain power bound or power limit or some constraints in terms of energy and power usage on the site. Those constraints have to percolate hierarchically below, right? So eventually you want to make it all the way to the node. So those site level constraints need to be handled by the resource manager or the job scheduler on the supercomputing center. So you now need power aware job scheduling, which is the second level in the hierarchy here as you move towards the right in the figure. And the role of the power scheduler here would be to set a job level power bound and allocate nodes to a certain job. Within the job, you can still have load balance, and you can still have load imbalance, and you can still have scenarios where you want to give some tasks of the job a higher power bound and other tasks of the same job a lower power bound. This can happen in workflows, this can happen in load imbalanced applications, this can happen in terms of performance tuning to make the critical path of an application faster. So that's application level power tuning. And finally, to be able to enable all of this, we need the bottommost layer, which is the component level measurement and control at the node level, right? So this includes your CPU, DRAM, GPU, other components that might exist on your node. So management of that power. There's also the idea that you need application power profiles. So being able to use historical information from the application to inform application level or, power like job scheduling level or the application level performance and power tuning. So this picture here captures a full systems effort or integrated effort towards management of power at a supercomputing center. A set of academics, research labs, and industry collaborators came together and said that, hey, we need to standardize this, we need to homogenize this. So there have been two parallel efforts for this. HPC Power Stack is one of them. It's a community effort on, basically understanding these different levels and interactions between them. And then the second effort is Power API, which comes out of Sandia National Labs. Both of those efforts are quite synergistic and complementary. So they work together, one focusing more on what the API and interfaces look like, and the other focusing more on the engineering aspects like granularity and data packaging and so on and so forth. So there is a link here to the HPC Power Stack if you are interested at the high level on in understanding the system level power management. The focus for Variorum is at the component level. So it is a platform level library to expose knobs across different architectures. So that's what we will be focusing on today. And we will touch a little bit on scheduling and runtime systems, application level runtime systems in module 2. So like I mentioned, PowerStack is a set of industry, academic, and research collaborators across the globe. So we have lots of industrial partners. We have collaborators across Europe and Asia. We have all the national labs coming together. There are 3 working groups within this at the 3 different levels that we showed, the scheduling level, the runtime level, and the node level, or the platform level. And they discuss primarily dynamic power management and site level optimizations. So one of the PowerStack prototypes has been developed as part of ECP Argo, which uses Slurm, GOPM, and Variorum. And we will, this is developed in close collaboration with Intel at some point. And we will talk a little bit about this in this lecture series as well. There is some additional prototyping that is going on with Flux, which is an in-house resource manager developed at Livermore, and Variorum that is underway. As I mentioned, there are different levels of the PowerStack. We already talked about this. We have site, system, and platform. So these are 3 different groups that are being managed, and you can look at the PowerStack website to find out more. There's also idle and emergency power management, which is being discussed as part of the PowerStack, the broader PowerStack group. Let's bring the focus back from that community effort to ECP Argo, which is collaboration between Lawrence Livermore National Lab and Argonne National Laboratory. So this is a more limited group of people and researchers as part of ECP trying to contribute actively to PowerStack. So ECP Argo uses Slurm and Flux, it uses Intel's GOPM technology, and it uses Variorum as vehicles for power management at exascale. So the goal here is to develop that PowerStack with these known components and interfaces between these components. So here's a very simple figure that captures that. Let's say you have a job queue, you have a scheduler, it allocates the jobs out here in a power aware manner, and that can be done with Flux or Slurm, or even a PowSched tool, which is developed by Daniel Ellsworth, who's now at Colorado College. So you can do low overhead, coarse-grained power management at the scheduler level. And then we can, we take a deep dive into a single job where we can attach something like Intel's GOPM, and we can provide more fine-grained application level load balancing and tuning. And in order to support diverse microarchitectures within that framework, we would need something like Variorum to expose all the different knobs across, say, Intel or IBM or AMD and all these different platforms and microarchitectures. So that's the big picture as to how ECP fits in, and it fits into the PowerStack and what the PowerStack community is doing. And now let's look at some data and numbers. So this is data from a supercomputer at Lawrence Livermore National Lab. It used to be one of the top 10 supercomputers back in the day. It is called the Vulcan supercomputer. It was a BGQ supercomputer. And I think what this graph is really showing is power on the y-axis in megawatts, and time or across almost 5 years on the x-axis. And we are looking at 3-minute samples of power consumption on this particular supercomputer. The procured peak power on this was 2.4 megawatts, which is the dashed line that you see at the top. And the average power consumption across the entire 5-year window was about 1.47 megawatts. And as you can see, there were times when we had maintenance cycles, which is when the power drops to 0. There was some initial burn-in phase and running of high-performance LinPack in the very beginning, where you can see the power go up to 2.3 megawatts or so. But other than that, the average power consumption for the workloads that we had was pretty low. So we had a lot of capacity that was that could have been used better. So we had about 40% of unused power here. And even though the node utilization was 100% and the supercomputer was very highly utilized in terms of its compute hardware, it was not very well utilized in terms of power consumption or power infrastructure. So we looked at this and we were like, why is it this way? And what can we do better? So let's look at why it is this way first. So this graph is from Daniel Ellsworth, and he is now at Colorado College. I should update that slide. And he studied different applications under power caps and tried to look at what happens as we start capping power and how do the applications behave in terms of performance. So the data that you are seeing here is from Intel Sandy Bridge. It is a little bit dated, so it is from probably 2014 or so timeframe. And the key thing to note here is that we have what's on the x-axis, relative runtime on the y-axis. And as we go from right to left, so the way to read this graph is go from the right-hand side on the x-axis all the way to the left to look at how the application slows down once you start power capping, right? So the rightmost point is no power cap, the leftmost 50-watt point is very extreme power cap, like a very low power cap. And as we can see, there are applications that do not slow down, So there are a few, I'm not sure if you can see my mouse pointer here, but there are a few applications here that do not slow down, even if you drop the power to 50 watts per node, right? So, and then there are other applications that slow down significantly with respect to power caps. So essentially, the point being, different applications have different memory, communication, and I/O requirements. They have different phase behaviors. And a lot of the applications don't utilize all of the allocated power. And always, like at all times, allocating more power to an application doesn't always improve its performance. So this was a key finding in understanding that graph that I showed earlier, which was this one, which is, we have a lot of applications at the lab or in DOE labs that do not utilize power very well. And this is because they tend to be more IO and memory bound. In some cases, they have a lot of phases where they're compute bound initially, and then they have an IO or a memory bound phase, right? So that kind of leads to this sort of, what looks like underutilization of power infrastructure. So as a result, it is important to pick the right configurations and the right performance and power points for energy efficiency. And we've done, this team here, Anirudh, myself, Stephanie, Barry, and even our collaborators from Argonne, Kamil, Swan, and Kaz have done a lot of work in this area in terms of understanding what do runtime configurations look like, and how do we pick the right number of threads, the right number of processors, the right number of the right power cap to identify what's the best way to run this particular job under a power bound. A very simple example of this is, this one application called SPMZ, which is a NAS benchmark. And let's assume we have a 4,500 watt power bound. And this spider graph that we're looking at here, it looks complicated, but it's quite simple to understand. We are kind of interested in two output parameters. So execution time in seconds and average watts in basically, the power consumed by the application. This center point here is 0. So essentially we want to pull down on the seconds axis. So we want to, run the application in less amount of time, right? So for the application to run faster, we pull down on the seconds axis, and we want to push out on the power axis. So we want to consume as much power as we can while executing as fast as we possibly can. And then we want to look at what configurations, so nodes, cores per node, and the processor power bound leads to that, right? So the red one here shows the default, which is we run all the cores on the node. So this is 0, this is 16 cores. So this is 4, 6, 8, and so on up to 16 cores. And there's 5 different power bounds here. So the traditional configuration is the one highlighted in red, where we run all cores, maximum power, and a limited set of nodes that we can bring up under that power bound. And it leads to a certain time and a certain power consumption. The better configuration we found was when we drop the number of cores, drop the processor power bound, but are able to bring up more nodes under the same power cap. And that results in a 2x speed up. So this work was done back in 2013, essentially showing that configuration selection is critical for power and energy efficiency. And in some cases, we can do this where we can change the configuration of the application. In other cases, we can't. We have a similar result here for Lulesh, where we are looking at different number of threads here. And as you can see, there's a Pareto frontier here, which shows what the optimal number of threads at each different power cap is. And we can point you to papers that discuss both of these results in case you're interested in more detail. The other issue here that we wanted to bring up, or another challenge in the power space, is that of performance variability, which results from the actual manufacturing process in the processor manufacturing area. So this is data from Anirudh's paper. The y-axis here is normalized IPC, which is instructions per cycle, and the x-axis is processor power in watts. Again, the way to read each of these charts is to go from right to left. So on the x-axis, so you can kind of see how things slow down, or how applications slow down over when you change the power caps. And we are showing two different architectures here. There's the Intel Sandy Bridge and Intel Broadwell. And the thing that we notice is that when we run the same application on different nodes in the cluster, we see significant variation in performance. And we'll be showing a demo regarding this shortly, which kind of explains this a bit more. But essentially what happens is every single processor behaves differently under a power cap, especially at extreme power caps when you're looking at like low power caps of, say, 50 or 70 watts on these particular architectures, right? So they start off having very similar performance here. And then like some processors are faster, like these guys are some processes are slower, so these guys are slower, and some processes are faster. So there is a significant difference in performance, creating load imbalance, which also makes it necessary to have something that does dynamic power balancing. So this is not just an Intel issue and not just a Sandy Bridge and Broadwell issue. All of our vendors have confirmed that manufacturing variability exists in hardware, and it continues to increase as we pack more cores and GPUs onto the same node. And there can even be like a 4x difference in performance between processors at some points in time, depending on the application that we are looking at. So with that, let's look at a short video here. I'm not sure if it's already showing up. Can you see the video, or do I need to share it separately?
I think you have to share it separately, Chapathia.
Yeah, let's do that. Stop share and okay. Is that visible now?
Yes, we see it.
Okay, great. So let's walk through this one simple example of basically how variation impacts performance. So what we are looking at here is a very simple script that's going to set power on different on the good and bad nodes that we already know or we've identified on one of our clusters. And then we are going to look at how execution time varies with different power caps. So the default on this node is 120 watts per socket, which is the maximum. And we already know that node number 498 and 1848 are they are the good nodes, they are high performing nodes, and that nodes 294 and 1380 are low performing nodes. So we've already done this characterization for this cluster. And we'll be looking at 3 different power caps, 120 watts, 105 watts, and 60 watts per socket. This is an Intel system. So this is an Intel Broadwell system with 36 cores and 2 processors per node, 18 cores per processor. So I'm going to fast forward this a little bit because I think I know where my stopping point is. So we've looked at the script. So essentially what the script is going to do is set 3 power caps and then, show us the time. Should take about a minute for each of the runs here. And we are running the LU application class C. This is a NAS application, which is quite well known. So let me fast forward to the point where we actually see the result. So here's the first one, which is at 120 watts. Right, so we see that the good nodes took 19.7 seconds, the bad nodes took 19.95 seconds, which is not too much of a difference in performance, right? At maximum power, there is not much of a difference in performance. Let's look at what happens when we change the power cap. So now we are looking at the second power cap, which is 105 watts, which is getting set here. And as you can see, we set that power cap. I'm going to forward again to look at final numbers here. And this time, the good nodes took 20 seconds. The bad nodes took 21.8 seconds. So there's a bit of a performance lag at this particular power cap, right? So if you had the application if it was spread over the good and the bad nodes, you would be limited by the performance of the bad nodes in this particular case. Because if you had an MPI application that was, spread across these, then you would have the slower set of nodes being a barrier. And let's finally look at what happens if you set the power cap to 60 watts. And that's been set here. Let's move on to look at the actual time difference here. So here you can see that this is a more significant difference. So it goes from 29 seconds to 36 seconds, right? So the good nodes are performing almost 7 seconds faster at that particular power cap than the bad ones, and this is a problem in a lot of ways, right? Because now you've created an imbalance in an application that did not exist before. So if you were not using a power cap, you would be getting around 19.9 seconds on both sets of nodes, but under a power cap, the performance variation can be significant. And this is one reason why power management is quite challenging. Let me stop this and share my slides again here. Okay, the other issue that we have been looking at.
Tapazia, your slides aren't visible yet.
Oh, hold on. That's weird. Are they visible now?
Here you go. Mm-hmm.
Okay, sounds good.
Looks
So
good.
so we saw the demo on performance and processor variability. Let's go into, I'm just looking at time here, so I'm going to speed up a little bit. And let's look into workflows. So this is an example of what happens in a workflow if we were trying to manage GPU power. So we are looking at the MUMI workflow here, which is cancer biology workflow that does like multi-scale machine learning to identify proteins and mutations. And this study has been done on the Larson and Sierra supercomputer. So here we see something very similar. We see that one of the key components, the key compute components, which is a GPU component of this particular workflow, if we start doing the same thing, set a power cap, and then look at performance on the y-axis, we notice that there is no performance slowdown going from 300 watts on the GPU to 175 watts on the GPU. And after that, we start seeing the same trends in variation that we saw on the CPU. So this exists on the CPU, that exists on the GPU. The other thing to note here is that if you just started capping all your GPUs for this particular application to 175 watts, you would have the same performance and you would save like 382 kilowatts on this particular supercomputer, which translates to about 43,000 cost savings per day if you were paying 7 cents per kilowatt hour. So this was an interesting result for us in terms of even electricity pricing, as to figuring out that power capping can also help you save energy costs for your supercomputer. And then there is the final issue here of mitigating power swings. And this is an important aspect as well. So the graph here is showing data again on Sierra at full scale for this application called LBAN, which is an artificial neural network application. It utilizes all 4 GPUs on this Sierra node, and we are looking at 3-minute time samples. What we see in a 6-hour run on Sierra is that there are power swings of about 200 kilowatts every time there are some synchronization operations happening within the workflow. And we've noticed this sort of a trend even with other science workflows. So there is a need to even mitigate the power fluctuations to avoid any electrical supply disruption, right? Because if you had these swings to go up to a few megawatts, that is also going to be a problem. So if we are looking at, say, the next generation of supercomputers at exascale, that 200 kilowatt swing would look like a 1 megawatt swing, which is a problem in terms of grid stability and reliability. So all of these aspects require power management at the node level with enabled through schedulers and runtimes, but more importantly, having the component level mechanisms to do so, which is what Variorum does. So let's dive into how different architectures even manage power. So we'll look at measurement and control. There are 2 primary mechanisms. One is DVFS, or frequency scaling, which used to be quite popular in the past. And more recently, a lot of the architectures are supporting power capping. So there are techniques such as RAPL, running average power limit, which Intel and AMD uses. And then there is the Opal firmware open power abstraction layer from IBM. And then there is NVIDIA's NVML library. I forget what that stands for, but NVML also allows you to control power for NVIDIA GPUs. We can also do some tuning of the turbo frequencies. So you have Intel Turbo Boost, AMD has a boost limit, and IBM has Ultra Turbo. There are some details here about ACPI and DVFS and RAPL and Opal. The key takeaway point here is that each of these techniques is implemented differently. For example, DVFS is expressed, it's basically setting the CPU frec, and it sets the frequency of the processor a certain way. RAPL, on the other hand, sets a power cap using a power window and a time window, and it does so by programming machine-specific registers. So this is what Intel and AMD use. And Opal provides a sensor-based mechanism for power monitoring and an out-of-band mechanism through their BMC for power capping. And we will look at each of these in like a little bit more detail now. So let's start with Intel's RAPL. So Intel provides programmable machine-specific registers for power, energy, and thermal management. There are different domains on which you can control this. So the package represents the processor cores, the caches, and other things on the socket. The DRAM represents the memory components, and there are some other uncore components that also are exposed through these MSRs. And here's an example of a specific MSR called package power limit. And here you can see that you have the option of setting a time window and a package power limit. And then you have another option of setting another time window and another package power limit. And by programming this kind of a register at the lowest level, you can actually enforce a hardware-based power cap and ensure that your application runs within that power cap on Intel systems. A similar mechanism is used in AMD, but we will talk about that in a bit here. I am going to skip this demo in the interest of time, but we can play it at the very end if we have extra time left. It basically shows tools like read MSR and write MSR, which are from the Linux kernel development community, and they can be used to program these particular MSRs by specifying the address and the actual hexadecimal or hexadecimal values for these particular fields. So let's look at IBM now. IBM has a primary secondary design, and it has an on-chip controller as well as BMC here. And essentially, the OCC collects data every 250 microseconds. The power knobs for control are exposed through the open power abstraction layer, Opal firmware, and essentially the OCC primary here will be responsible for system power capping. And IBM does not expose any socket level power capping. So Intel here, like we said, the package here represents a socket, right? So all of the registers, most of the registers are at the socket level. IBM does this at the node level. It also allows you to specify GPU power management through a unique feature called power shifting ratio, which determines the power distribution between CPUs and GPUs. And like, as I mentioned, per socket or memory power capping cannot be specified. The primary OCC has control. And here's a picture that nicely shows the limits on the IBM system, the Power 9 system that we have, at least at Lawrence Livermore, which is a system with 4 GPUs on it. And then you have a soft power cap, you have a hard power cap minimum, and you have a maximum power limit. And Opal uses in-band sensors for exposing different power values. There are over 336 sensors that are reported, and these include things like power, temperature, frequencies, and for both CPU, GPU, memory, all of that. And for Opal firmware, these are the files that are exposed through sysfs, and then we can write to those files to program them to let Opal know how to set the power cap or the power shifting ratio. AMD uses something known as the ESMI library in conjunction with the AMD energy driver and the AMD host system management board, or HSMP. These are all open source, so you can look at them. In terms of the energy driver, this is very similar to what we discussed for Intel's RAPL. So this allows access for core and socket energy counters through MSRs. These are mostly for measurement. So these, unlike the Intel RAPL registers, this is primarily focused on measurement. So you can measure the core energy, you can measure the socket energy, and they are updated every 1 millisecond, which is also the same for the Intel system. The HSMP driver allows for power capping and setting of boost limits and PCIe access. So that's the mechanism that AMD uses for control. And it has a mailbox approach for register access internally, and it also exposes these through sysfs. So you can look at, you can basically set power through the sysfs interface on AMD. Note that we are not talking about AMD GPU management here. It is available through the ROCm SMI, but we have not, as a team, explored it much, so I can't go into the details here for that. And with that, I'm going to, actually, I have one more slide. So here's the sysfs interface for AMD Power Control, and this is, again, exposed through the HSMP kernel module. So you have the boost limit, which is at the CPU level. So this is possible for each particular core. And then you have a lot of these fields for the socket level. So you have the boost limit, as well as, power limit and thermal control value, and these kind of different values that we can set at the socket level. So AMD exposes a lot of the same or similar knobs as Intel does, but this is exposed through, the control knobs are exposed through sysfs. I will stop there and transfer it over to Anirudh.
You can, if you want, you can continue to, broadcast, and I will just go over the next slides.
Okay, I can do that. I'll be on mute, and you can just tell me when to use the next slide.
Okay, great. Am I audible? I assume I am. So in the next 3 slides, I will go over the measurement and control interfaces on the ARM and NVIDIA platforms. So the ARM implementation that we support with Variorum is the ARM Juno R2 platform. The figure here shows the different components on this platform. So it has 2 types of clusters or processors. The dual core Cortex A72 MP core or the big cluster that supports higher frequency steps, and the quad core Cortex A53 or the little cluster that supports lower frequency steps and also has a GPU. It supports different kinds of measurements and control of the 3 processing units and the entire SoC as well. And that's provided through the system control processor or SCP subsystem. So the Variorum port that we have leverages the temperature, clocks, and energy telemetry exposed by SCP, and also uses the DVFS controls on the big and little clusters. So for reference, you can see the ARM Juno developer documentation. Next slide. So the Variorum implementation on ARM leverages the sysfs interface through standard Linux HWMON. Specifically for power telemetry, the HWMON interface exposes 4 power registers provided by ARM Juno platform. These provide the entire system or SoC power usage along with the power usage of the 3 compute components. The sysfs interface also provides the temperature sensor measurements in degrees Celsius. For clock measurement and control, Variorum leverages the standard Linux CPU FREC interface. And the system also exposes these interfaces separately for both big and little clusters on the SoC. Next slide. For the NVIDIA platform, Variorum leverages the NVIDIA Management Library or NVML interfaces on the GPU accelerated systems, that system that Tapasya mentioned, specifically the Sierra system with Power 9 and 4 Volta GPUs. Currently, Variorum only supports measurement for the GPUs, and it does not support control. This is specifically due to the limitations of the configuration of the target platform we have. The power telemetry is of 2 types. First is the instantaneous power usage. Second is the current power limit assigned on the GPUs. Both are in watts. These are obtained using the NVML device get power usage and NVML device get power management limits API. The temperature is obtained using the device get temperature API in degrees Celsius. The streaming multiprocessor clocks are measured using the device get clock API. This is in megahertz. And the GPU device utilization is measured using the device get utilization rates API. This specifically provides the occupancy rate for the target GPU in percentage. So with that, I will hand it over to Stephanie for a deep dive into Variorum.
Right, and I'll stop sharing, Stephanie, so you have control at your end.
Sounds good. Thanks.
Mm-hmm.
Okay, let's stop. Okay, so now we're going to transition over to an overview of Variorum. So Lawrence Livermore, specifically this team, has been particularly interested in exploring power and energy control knobs over the last several years. And particularly, we're trying to understand what the impacts of tuning these knobs is on our applications. We started an open source library known as libmsr. Some of the folks on this call may be familiar with this library. This actually started back in 2012 as a summer internship research project. And I think with some of the examples that we showed, trying to write and set the knobs of some of these registers can be quite tedious. We're trying to set the individual fields within these 64-bit registers that we had shown on previous slides, and it can be quite error prone. And so one of the goals with us developing libmsr was to provide these nice interfaces so that we could easily set the power limit into bits 0 through 14. We could toggle the power limit to on and off by just passing these parameters into the functions instead of having to manually do it by hand. And one of the videos that we didn't get to show kind of shows you how tedious it is to write out this hex value into the register. But one of the challenges we have with libmsr, especially as we start looking to more heterogeneous systems, is that libmsr was Intel specific. We had started it back with Sandy Bridge and had kind of just ported it to continuous or to newer and newer Intel architectures. But as we start to see these newer devices and different devices across the board, we weren't going to be able to continue supporting libmsr. As we looked across the different devices that we might see within our systems, we started to see that the features not only differed across the devices, such as the interfaces to control and monitor the power and energy usage, as we had just talked about in the previous slide when we looked at the knobs and controls across the different architectures. We also start to see differences in the domains of control in which these knobs impact. So some are impacting just at the node level, some are impacting at the socket level. And even further, we start to see differences in the speed or the latency in which the hardware actually reacts to the enforced power limit. And additionally, one other piece to further complicate this problem is that some features might exist on some systems, like the power shifting ratio on IBM systems, but we might not see that on other architectures. So this table here on the upper right is just giving, showing the differences that we see in different features across different architectures. So for this particular example, we're looking at 2 generations of Intel processors, looking at Ivy Bridge, which is an older system, and then comparing that against Haswell. And if we look at the CPU frequency implementation of these 2 generations, on Ivy Bridge, we were seeing it impact at the per socket level. And then when we moved to a Haswell system, the CPU frequency is impacted at the per core level. When we look at energy status or energy usage, when we want to translate the units out on Ivy Bridge, there's this energy unit that's been fused into another register called the MSR power unit, and you use that value to convert into joules. And then when we moved to Haswell, we actually didn't want to use the value in the MSR power limit, even though that was available. But in reality, we needed to use this other standard joules value that was defined in the Intel standard. And then when we looked at power limit, you can have the same implementation. So this is kind of just trying to give you a flavor that we're trying to address the different architectures. We're trying to address these different interfaces, domains across the different platforms. So instead of having, now I'm going down to this figure on the bottom, instead of having an implementation for these different features like power monitoring, power capping, energy usage, and frequency for the wide variety of hardwares that we're seeing in our systems, we're proposing to have Variorum be that center hub so that we can implement all of these different features, all of these different use cases for these different platforms that we're targeting. So additionally, our goals with starting Variorum were to first provide APIs that are targeting what we're calling our 95% of users. So for those who are more familiar with libmsr, that was much more close to toggling bits here and there. What we're trying to do with Variorum is abstract a lot of that layer away from the user. So these might be users that are just concerned with, how much power did my application consume on this machine, right? I might not be concerned with, oh, how did, my processor implement the frequency or the energy usage. I just want to know how much power I'm consuming. We obviously want to be targeting additional devices. We're covering CPUs and accelerators, but further down the road, we have plans to support IPMI and PCIe devices. We also want to be able to support platforms and architectures, and we're kind of using platforms and architectures interchangeably here, but what we're after is multiple generations within the same device. So like Ivy Bridge, Haswell, Skylake in the Intel line. And we also want to expose additional hardware knobs and controls. So we've been very focused on power management, but we obviously there's other knobs and controls that we want to expose to the user as well. So Variorum is a vendor-neutral user space library for power management. It's providing platform agnostic, friendly, easy to use APIs to the users. Again, Variorum is essentially an evolution of libmsr, which was targeting several generations of Intel processors. So a lot of that functionality, if you're familiar with libmsr, has been brought into Variorum to cover those architectures. We have designed Variorum to target several platforms that we kind of covered in the beginning: Intel, IBM, NVIDIA, ARM, and AMD. We've supported those in Variorum and designed the front-facing APIs in a generic way so that they can interface with the different architectures and the different features that they support. As I mentioned, we support, as our latest release, which came out in April, we support 5 different platforms, as well as their mechanisms for power management that were previously discussed by Anirudh and Tapasya earlier in this presentation. And just to recap, I guess, some of the underlying monitoring infrastructure that are being used for Intel platforms, for Intel and for AMD, we're going through the running average power limit or RAPL interface. AMD's got the ESMI interface that was talked about previously. For IBM support, we're using the Opal firmware. And for NVIDIA, we're using the NVIDIA management library. And for ARM, we're going through HWMon or the sysfs interface. Oops, sorry, advanced too fast. Let's see. So Variorum's implemented in C, and the way that we do this under the hood is we have function pointers in a struct that target the particular architecture on which it's built. And as you kind of saw on the next slide, we're going to do a demo of what the build for Variorum looks like, so you can kind of get an idea on how you might build this for your particular architecture. We've also extended Variorum recently to be able to integrate with higher level power management software through a new JSON interface, so that you can pass values along to another actor and have them do something with those power values, or and have them do something with the metrics. So this bottom right figure here is showing the system architecture for Variorum. So this box in red is highlighting where Variorum sits in the system architecture. So we are giving a snapshot of some of the high-level interfaces that we're currently providing in Variorum. So the idea is that these functions are, regardless of what architecture you're on, we will do our, we will go through the interface that's particular to that architecture in order to return to you those values. So we can print the power, print your available frequencies, whether you're on the CPU or the GPU. And then we also have capping interfaces for capping the socket power limit. And then this last example is showing you our high-level API for getting the node power in a JSON object that you can pass along. And so the remainder of this system architecture diagram is showing, Variorum sits on top of these kernel interfaces that the different architectures provide. So with Intel, we've got the MSR safe kernel module that Livermore developed and has deployed on some of our systems, as well as several systems across the globe. If it's IBM, we'll go through the Opal layer. For NVIDIA and ARM, we'll go through NVML and HWMons, respectively. And then below that are really the low-level control knobs for the particular architectures. So here in blue are those 5 architectures that we currently support. And then down in our roadmap, we have plans to support additional hardware such as InfiniBand and IPMI to get further metrics and expose more knobs to the user. Okay, so I'm going to switch to a demo. So the first one is going to walk us through the build for Variorum. So this is the top level of the Variorum directory. If you were to clone it straight from GitHub, I'm going to point us at the source directory, and we're going to take a look at the high-level CMake lists. So there's some options for building the documentation, building shared libraries and tests. We provide Fortran for some of the examples in Variorum. But the key variables that you'll be wanting to toggle on and off for your particular architectures are these ones that are highlighted, these Variorum with, and then whatever the architecture is. So for this particular system, which is Octomore, this is an Intel-based system. So you can see that we've turned on, our Variorum with Intel variable to build for an Intel system. And what Variorum's doing is once you point it at the particular system, it's going to go ahead and read some of the machine level information to determine which SKU is it that you're building on. Is it a Skylake system? Is it a Broadwell system? Octomore, I believe, is our Skylake system, and so that's what our CMake file is going to be running. Also in Variorum, if you don't want to use the high-level CMake lists, we provide host configuration files for some of the different systems that we've talked about, like our Juno board, which is ARM, our Lassen system, which is our CPU or IBM system, as well as different Intel platforms. So for our Octomore system, this is what the host configuration file looks like. And so we've got it pointed at a particular HWLock and JSON installation, which are dependencies of Variorum for getting the system architecture and for enabling our JSON API. We're going to set this Variorum with Intel to be on. This use MSR safe variable is to distinguish. We have, as of our latest MSR safe release, we've moved to the new name is the MSR allow list. So this toggle is looking for either the MSR allow list or the MSR whitelist, which was in the 1.4 release, which some of our systems are still deploying. So if we were to build this on other systems, like our Lassen IBM system, you'll see that what's changing is maybe the HWLock and the JSON library location, but really what's key to be changing is that you're toggling the with IBM variable on, or the with AMD or with ARM variable on to switch the function pointers to point at the correct implementation. So you'll see that our Juno one, we have the ARM variable turned on. And then for AMD, which we don't show here, you'll have the AMD one turned on, of course. And so we do an out of source build for Variorum. So we go ahead and make a build and an installation directory. We'll CD into our build, and then we'll run CMake using the Octomore host config file that we showed. So you'll see that Variorum comes with several examples, as well as this demo application called Palmon, which we'll get to in a few slides. I'm going to speed through this make. And a make install. Oops. So you can see once you run the make install, you've got your libvariorum library.so in your build directory. And you've also got it over in your installation if that's where you would like to point it at. Okay, so the other example or the other demo that I'm going to walk us through while we're here is showing our examples, a couple Variorum API examples running on our Lassen IBM system. So this assumes that you've already built Variorum for your target platform. You'll have your executables over in your examples directory. And we're going to first run the print power example. And so we put tags here so that you can easily grep and dump this into a separate file and then be able to use your favorite, R or Python to parse this into a graph. But what you'll notice as we compare against the other architectures for this example is that the headers will change based on what's available coming out of the platform. So for IBM systems, we get the power usage in watts for the different domains. So its domains covered are the system, the processor, and in this column, you get the memory power, and you also get the GPU power. And I think this timestamp is also coming from the Opal interface as well. So you get that read. Oops, just walking this through. So this next example is to show the power limits on our Lassen system. So our headers here now is what is the current power limit, also in watts. We're getting information about what the min and the max power is. And so this is key for when you're wanting to cap or set the power limit on the system so that you're within the proper bounds. The system, of course, should have some mechanisms to protect that you're not going too high of a power limit or setting it too low. But this can kind of help you if you tried to set to 250 and to 250 watts and you saw that, hey, the value that's actually in that register is 500 watts. You could see why that was the case. And then the other fields that you get with this print power limits, PSR is the power shifting ratio that IBM provides. And so we get it for both sockets. So the power shifting ratio of the CPU to the GPU is 100% dedicated to CPU for both of our sockets. Okay, I'll show this one. So one of the other APIs that Variorum is providing is this notion of a cap best effort node power limit. And we'll get into this on one of the next few slides. But of course, one of the challenges that we've talked about with Variorum is that features don't exist across all of our platforms. And so how can we define high-level APIs that might exist on one but not exist on another? So in particular, one of the things we've talked about is this idea of the node power limit, which is provided through Opal, specifically on Lassen or on IBM systems. And so we wanted to have an API so that you could cap the node power limit on IBM systems. Now, if we think about how do we cap the node power limit on an Intel system, of which not all Intel systems provide node level power limits. A lot of them provide only socket or package level power limits. If a user were to set the node power limit on an Intel system, it doesn't make sense, right? Because it's only capping at the socket level and not actually at the node level. And so we'll talk about in a future slide how it is that we're handling this. But just so that you can see how this example is run on an IBM system, we're going to cap the node power limit, which is this system level. This was at 3050. We're now capping it to 2000. There's a warning here that you'll see in the example, just letting you know that there's some latency for this value to propagate out of band. So if you were to run in a cap and then immediately read, you might not see the value be reflected. And so what we do is we wait 500 milliseconds or so in our example, and then we will print the power limits again, so that we can see that that value actually got reflected. So she'll run the print power limits, and now you can see after some time, the power limit has changed to 2000, which is what we specified. Okay, let me switch back to slides. So what we showed in the demo was additionally to the Variorum build, we're also showing some of the examples, and these in particular that we were showing, the print power example, the print power limits example. These are source code annotations that you can put into your application so that you could measure end-to-end power usage around your loops, or just end-to-end power usage of your entire application. So what we're showing here is the print power example that we had shown on IBM. That's this here in the white. It had the system domain, the processor domain, the memory, and the GPU domain for IBM systems. We're also showing that same example running across the other systems that we support. So on Intel systems, they have the package domain as well as the energy or DRAM. Sorry, they got the package domain and the DRAM domain. And what's different about Intel systems is that they're providing the actual energy usage, or they're providing the energy consumption in the register. And so it's this register that we're reading in Variorum. And in order to convert that to power, we're reading this value twice and then taking the difference over the time elapsed between those reads. And so that's kind of why you're seeing, for in particular the package energy, you're seeing the initial read of the energy at this particular timestamp, and particular watts will be 0. And then we read the package energy again in order to convert this to watts. On NVIDIA systems, you get the power usage per device. So on our Lassen system, which has 4 GPUs per node, we're seeing, where's my mouse? We're seeing 4 different entries, 1 entry per device, or 1 power reading per device on the Lassen node. And then for ARM, when we print the power example, their domains are the system, and then they have this notion of a big and little core that they're printing the power now in milliwatts here. And then the other domain that we have access to on the ARM system is the GPU. And so you'll get the power value for that. But you can kind of see that we've adapted the data while you're running the same example across all of these architectures, and you're getting the same, virtually the same data, at least in terms of getting the power usage. The way that we're printing it out is very specific to the particular architecture and the features that it's providing. So the other example that we showed in the demo was how to cap the power. We actually were showing cap power, the cap best effort node level power in the IBM demo video. But here what we're showing is how to cap the power at the socket level. So on Intel, which provides a power limit at the socket level, we can run our example and cap it at 100 and see that this API is provided and does work. We don't show you the print power limits here. For IBM, this was the example we showed, which doesn't provide a socket level power cap, but does provide a node level power cap. For NVIDIA and ARM, what you'll get for these cap socket power limit example is this error from Variorum indicating that the feature either hasn't been implemented yet or that the feature does not exist on the platform. So we haven't yet tried to tease out those 2 differences in terms of the error message that you're getting. But for NVIDIA, when you do get this error message, this means that the feature does exist in NVML. We just haven't had a chance to implement this capability. This is a limitation of having the necessary privileges to actually set a power limit so we can test on our systems. And on ARM, this feature is actually not supported. So you're not able to set the power cap at the socket level. You're only able to do DBFS under the hood. Okay, so I'm going to do one more demo. And this is our a demo app known as Palmon. And this is for non-intrusive monitoring of your application. It's actually external to your application and doesn't require any annotations. So what we did here was clone the Lulesh directory just to use Lulesh as our example application. So we're going to go ahead and compile Lulesh over on our Intel Octomore system that we used in a previous demo, or I guess in our build demo. And we can see we've got our Lulesh executable here that's been built. And again, this assumes that you've already built Variorum. So I'm going to go ahead and show you where Palmon is located in the build system. We've got a Palmon directory over in build, and you've got a Palmon executable. There's also this other executables for power wrappers, dynamic and static, which were contributed. Actually, all these were contributed by Dan Ellsworth. Those are for setting either static caps or changing the power cap dynamically during the application. So we're going to go ahead and run Palmon for this demo. This is the menu page. It takes an argument -A, and then you put your application executable as well as any of its arguments in quotes. And you can also change the sampling interval if you like. The default is currently set at 50 milliseconds. And we've found that 50 milliseconds is, fast enough for us to see changes in the registers, but not so fast that we start to get really noisy data. This is just showing the arguments to Lulesh, so we can familiarize ourselves with those. And we're going to go ahead and run Palmon -A down here at the bottom of the screen, and we're going to put our executable and all of its input deck and parameters in quotes. So we just picked some various parameters so that the application doesn't run too long for the purpose of the demo. I think it's about 10 seconds or so. And you can see down here, after all of the application information, are these two lines here where we list which files were created by Palmon. So Palmon will create a file per host name that you're running on, or per host that you're running on. So you can see these here, and we'll go ahead and show you what's contained in each. So you'll get a summary file showing you what host, the process ID, when did you start, and how long you were running for. And then if we look at the DAT file, this is going to be quite long. So again, what we've done is, so it's a really wide array of metrics, right? So we're sampling the package energy for each socket, as well as any of the counters like instructions retired, unhalted clock cycles. We're sampling those per thread. And so that's why you get this really wide array of data. And so what we're going to do in future is try to be able to have users customize what metrics they're collecting in case that they don't want to see all of these metrics here. So I think I'm just walking through the files and the different samples that we're getting. And so this piece down here, one of the nice things or the way that we designed Palmon was that you can take that file and then throw it into an R script or a Python script and be able to convert all that data into nice graphs. So here we're just converting the timestamp into or I guess the timestamp and the energy readings into power readings. So we can get power readings for each package, as well as just compute what the total power was, or what the average power was for our application execution. I think we're going to run this and just print the different values. So that's just to show you how you might take this DAT file and run it through a script. So the screenshot is showing you what we had shown in the demo. This is just the top 2 lines of the Palmon demo over on Intel. We do have a demo of Palmon running on IBM, and you'll get slightly different headers specific to the IBM system and the metrics it provides. And again, once you run this through some plotter, you can make these nice graphs that we can show in future presentations and papers and whatnot. Okay, so we initially released Variorum back at Supercomputing 2019. And originally it came with support for IBM Power 9 systems, as well as a variety of different Intel systems that we had pulled in from the libmsr support and extended a bit. Our latest release was in April of this year. And we've since added support for NVIDIA Volta systems, as well as the ARM Juno SoC. There's also a PR for supporting AMD systems, and this is currently under review and testing. The other thing that we added recently was this JSON API, and this enabled us to integrate Variorum into external tools such as Cocos and Flux, which we will be talking about in more detail in Module 2 next week. So one of the things you might notice is that many of the APIs in Variorum are for printing our output to standard out for the user to parse and to understand what's going on. We think that while this is nice to have that functionality for our users to just understand the hardware level metrics, it does limit Variorum's ability to provide these metrics to another tool so that they can use it to make its decisions. So this is why we added a JSON interface to Variorum, and we're starting to build this interface to be vendor neutral, of course. And so our use case here was to provide it in the get node power JSON interface here. This is the API that we created. And currently our JSON objects are the host name, your timestamp, and then we get the power usage for the different domains. And this is still under development as we kind of try to extend this to be more vendor neutral. So as an example, we have integrated this into Cocos so that you can report end-to-end power usage on your Cocos loops. Another example for Variorum's integration was to provide power awareness into Flux, which is a scalable and portable resource level manager. And so now with the JSON interface, we can enable Flux to take into account the power usage when deciding how to schedule its resources to different jobs. And again, more details about how this all got implemented will be in Module 2 next week. So one of the challenges that we've been trying to address in Variorum is how do we implement a vendor neutral node level power cap interface? And specifically, this is a challenge because not all of our devices provide an explicit power knob for the node. So as we had mentioned before, IBM Power 9 systems provide a node level power knob through the Opal interface. But we find that it doesn't apply to all of our systems. In particular, Intel only provides us a socket level power knob for some of the generations. I believe some of the newer Intel systems are providing node level power knobs. So how do we handle this case of one system providing an explicit node level power cap and other systems not providing explicit, but we could maybe approximate the node level power cap on an Intel system by adding the power usage of all the different components that we know about or that we can get access to. So the way that we've currently implemented this is to provide this cap best effort node power limit, which we showed in an earlier example. And so if you were to run this on an IBM system, you're going to get the power cap that's provided to you through Opal. So it should be very exact and work as you intend it to. And if you're running this example on an Intel system that only provides a socket level power cap, then what we do currently is to take that power cap and uniformly distribute that across the nodes or across the sockets in your node. And for now, we're ignoring the memory and the end core power. So there can be a bit, if you're using node level power limits to make decisions, if you're using node level power limits to set a cap on a system or on a node, for an Intel system, you're going to have to add a little bit just in case that the other components end up taking more of the power consumption. Okay, I've got 5 minutes, so perfect. So a plug for next week. First we want to thank everyone for joining us today in our module 1 of the ECP tutorial series on Variorum. We're going to be running a module 2 of 2 this time next Friday, August 13th. And we're going to be looking specifically at how we integrate Variorum with different system software and tools. We'll talk about our GOPM integration, our integration with Flux and Slurm, as well as with Cocos. And if you have colleagues or you'd like to, there's things that you want more information on, we're going to repeat these modules again in weeks 3 and 4. And with that, I will open it up for questions if there are any.
So I have a question. This is Sid. Great talk, guys. Thanks. The earlier slide surrounding what do you do when a given vendor doesn't support node level power cap. The question there is, so how are you guys managing the power reporting though? So you did mention something along the lines of just make sure that the power value that you're capping for, you make sure that there's an extra headroom there just in case other components on the platform consume that power. So is there any best method or good recommendations on how much extra do you assign? Or because right now, if you do a power cap, do you, for example, take that value, cut it down by 20%, and then use that value and use RAPL to set that value on the sockets? Is that what you do?
No, so for now, we're just, we're taking what the user has given us in that cap best effort node power limit for Intel. So if you gave us 100, we're going to split that direct and give you 50, assuming you have a 2-socket system, of course. I think there's a good model to have, take a bit off of the top, right? So that you do give them headroom in case, things go south and things start to consume more power than you expect. But we don't have a magic number for that. I think users will be surprised if you under the hood took away 20% and set the cap to something different. But yeah, certainly it needs to be accounted for because if you're trying to set, a node power limit that you think you're setting and that's not truly what you're setting, decisions downstream could be heavily impacted.
Right. Okay. So so the value that the user enters divided by the number of sockets on the system, and then you just assign that. Okay.
Yep. It's a straight through.
Thanks.
Hi, Stephanie. Here's Torsten.
Hi, Torsten.
Could you make that user provided number that thing you subtract? Because I think system vendors might actually know what that could be, and we could put that in as a default setting or something, rather than you just assuming something and then subtracting it or whatever.
Definitely. Yeah, I think that's definitely a valid option is providing that additional parameter.
Yep, that would be
Yeah.
nice.
You know, in Variorum, one of the things we didn't get to today, but I think we'll talk about next week is, you know, there's the APIs that we currently provide is for this, you know, what we're calling a common user that doesn't care about the underlying architecture or have these, you know, very expert understanding of what's going on the different platforms. And so we're trying to think about how we might provide more advanced APIs, such as ones for, you know, system administrators that might know what that threshold should be, or folks that might want some of the underlying features of libmsr, like toggling the bits specifically to do a specific thing. So we might have different levels of Variorum APIs that we'll be providing down the road, and that might be one of them.
Thank you.
Mm-hmm.
One other question was, so to read and write into MSRs, is my understanding correct that Variorum still relies on libmsr under the hood? I mean, it's a fantastic piece of library, so.
Yeah, so for the Intel piece, you'll see a lot of the libmsr code under there. I think there's been a request to have some of that. Some folks were using some of those, you know, one of the downsides of libmsr is that if you were trying to integrate that into a code, you had to call init libmsr, then you had to, you know, allocate your necessary memory, know how many threads you were needing, et cetera, and finalize. So there was a lot of steps to make libmsr integrate into an application. That was pretty error prone. And so we've abstracted a lot of that away, right, by just having one function call into Variorum. One of the things that you don't get at, right, is the underlying libmsr function calls, right? If you wanted to allocate the memory by yourself, or you wanted to only set this one, you know, bit field to enable such and such feature. And so those are kind of some of the things that we want to provide access to, because we do have, you know, alongside the users that just want to, you know, do end-to-end power monitoring, and so on and so forth. We also have, you know, a big set of users, particularly in this community, that are interested in more low-level things that Variorum has kind of abstracted away. So we do want to support those users as well.
Great, thanks. I'll shut up and let others ask questions. I have a few more, but. Okay, while we do wait for others, by the way, others on the line, feel free to chime in. Just a few questions that I had. So you also did briefly allude to the fact that support for libmsr has temporarily been stalled, or not much active work is being done for the rationale that you did give for Variorum. But I was just wondering if there are going to be efforts by this team of upstreaming certain parts of that libmsr library up into the Linux kernel forum, right? So specifically things like the ioctl interface, right? And then the aggregation of telemetry.
You're talking about libmsr specifically, or MSR safe functionality?
Oh, the MSR safe functionality.
Okay,
right.
yeah, they're technically, yeah, so technically they're separate projects. Somewhat, you know, one is dependent on the other, and Variorum, of course, is also dependent on MSR safe. You know, Barry can probably speak more to this if he's still on the line, but you know, we've had discussions with the Linux kernel about trying to upstream some of the MSR safe functionality, like the batching interface, ioctl interfaces. It's been quite a challenge for us to try to get that integrated. A lot of us just don't have the bandwidth to keep pushing on it. And so that's kind of why it's stalled at this point. I guess, the MSR safe, we're still, you know, we still do maintain and we make changes. We had some summer students that were working on it this summer to make some improvements. But in terms of it going upstream, that's kind of been put on the back burner for now.
Understood. Thank you.
Are there any questions in the chat, Honorator Tapazio? I don't have it up.
No, I don't
Okay.
see any questions.
Yeah,
Sounds good.
any.
Okay. Sid, do you want to ask another question? We can just open it up for
I'll
discussion.
reserve it for module 2.
Okay, sounds good. Thanks, Sid.
Feel free to email us, folks. And Stephanie, do you want to just point them to read the docs and the GitHub
sure.
in case someone wants to browse through those things?
Yeah, and we actually did, we did get a chance to upload these slides if Osni doesn't beat us to it. So this is Variorum's Read the Docs page. We've got some information about how to build and the different APIs. If you're interested in porting Variorum to another architecture, we do have, we've got a developer documentation if that's something you're interested in. We of course welcome contributions and want to increase the different features or the different architectures that we support. So do visit that if you're interested. There are vendor notes down here at the bottom for the different architectures that we support, so that information about, IBM uses Opal. I'm curious about what those interfaces look like. NVIDIA, we've got more information about NVML. So this is kind of our landing page for the underlying hardware knobs and controls for the given architectures that we support, if you're curious. Under publications and presentations, we did upload our module 1 slides that we presented today. So you can go ahead and download those at your leisure. And we'll of course send our slides over to Osni so he can post those alongside this recording as well. And then, of course, we've got our GitHub page over in the Livermore organization, LLNL/Variorum. If you wanted to pull down our latest release or take a look through the code.